1943, June 17th, 04:30 hours. Somewhere off the coast of New Georgia, Central Solomons. The humid air hangs heavy and electric, smelling of fuel oil, salt, and the distant acrid scent of cordite. Below the lowering clouds, the sea is a disturbed charcoal mirror. Corporal Thomas Mackenzie, USMC, squints over the gunwale of landing craft vehicle personnel LCVP hull number 511, his knuckles white against the cold steel of the ramp mechanism lever. Mackenzie is not primarily a rifleman. He is a certified first-class shipfitter and field welder, a crucial cog in the logistical engine of the invasion force. His mission, right now, is survival, but his constant nagging failure is the very craft beneath his feet. The standard landing boat, the Higgins boat, is revolutionary in its function, yet tragically flimsy in its construction. Its thin hull, made primarily of plywood and backed by sporadic sections of quarter-inch mild steel plating, is a known liability. The low thrumming of hundreds of engines vibrates through Mackenzie's boots, a sound that paradoxically announces both salvation and slaughter. He scans the horizon, knowing the enemy positions on the beach are already sighted in, waiting for the predictable slow approach. 3 days ago, during the disastrous preliminary probe on Beach Red, Mackenzie witnessed firsthand the devastating consequence of inadequate armor. Field reports confirmed that 65% of casualties occurred in the final 300 yards of the approach, not from heavy artillery, but from standard Japanese heavy machine gun fire 7mm and 13. 2-minute rounds specifically designed to punch holes in light transport vehicles. Mackenzie's own landing craft took 17 hits to the bow ramp, transforming the area into a piece of metallic lace before the ramp even dropped. He shifts his weight, the heavy canvas jacket sticking to his back. The crew of LCVP 511 are silent, focused on the faint green light ahead that marks their vector. Mackenzie understands the constraints. Speed is critical, and any substantial increase in armor weight throws off the boat's trim, slows its speed, and strains the crucial mechanical ramp system. Naval architects argued relentlessly that adding enough ballistic steel, like genuine STS, special treatment steel, was logistically impossible in the field and structurally unacceptable for the shallow draft vessels. Mackenzie, however, sees the problem not in the weight of the steel, but in the efficiency of the field repair process. He watched a piece of scrap metal salvaged from a downed Zero, a thin aluminum fragment, ricochet a .30 caliber slug in a bizarre, unexpected way during a junkyard test last week. The phenomenon was momentary, unrepeatable, yet it planted a seed of violent dissonance in his technical mind. He looks down at his hands, calloused and scarred by heat, the hands that could fuse metal but couldn't yet save the men relying on his craft. The ramp clangs softly as the coxswain adjusts speed, and Mackenzie's focus locks onto the object resting beneath a coil of rope. A piece of perforated hull plating, dark with oil and corrosion, salvaged from the wreck of a sister ship. A grim, jagged-edged testament to the velocity and efficiency of enemy fire. It is not just damaged, it is utterly destroyed, riddled with holes that look less like punctures and more like violent inverted craters, each one representing a Marine who never made it past the water's edge. This piece of scrap, this fragment of failure, is the physical, sharp-edged center of his unresolved, desperate problem. The sound of the first distant mortar fire echoes across the water, and Mackenzie knows they are entering the zone, the space where engineering theory dissolves into sheer, brutal survival. The inadequacy of that thin steel is now a tangible, living threat to every man aboard. Mackenzie runs a glove along the edge of the salvaged hull plating, feeling the sharp, curled edges of the penetration points. His mind, usually linear and focused on the precision of amperage and tensile strength, is suddenly adrift in possibilities that defy naval doctrine. Why did the bullets punch through so cleanly? He muses internally, watching the faint glow of dawn creep toward the eastern horizon. The standard mild steel, often labeled as HTS or high tensile steel in non-critical naval applications, offers mass but little resistance to modern high-velocity rounds designed to tumble and fragment upon impact. He knows the naval engineering solution, true ballistic plating, is unavailable, requiring specialized rolling mills and immense production capacity, none of which is accessible here, thousands of miles from the mainland shipyards, surrounded by jungles and the constant threat of attack. The strange event had been the behavior of the shrapnel, or rather the lack of shrapnel. The rounds that passed clean through left minimal secondary debris, indicating they retained maximum momentum. Mackenzie began to formulate the idea not around stopping the round with impenetrable thickness, but defeating the round's geometry and velocity with confusion. This was not about metallurgy. It was about geometry and field expediency. He was a marine welder, not a physicist, but his hands knew what steel could tolerate. He imagined welding a second, thinner layer of ordinary scrap steel, easily acquired from wrecked trucks, supply depot walls, or even unused temporary decking. But critically, he envisioned offsetting it from the main hull by a mere 2 or 3 inches. This would create an improvised field-expedient, spaced armor system. The initial reaction from Lieutenant Commander Finch, the head of engineering repair for their flotilla, was predictable, outright incredulous disbelief. "Mac, you're talking about strapping junk onto the hull. You'll ruin the center of gravity and you'll invite rust pockets. It's uncertified, non-ballistic scrap," Finch had yelled, slamming a sheaf of outdated engineering schematics onto his field desk. Mackenzie's idea was radical, precisely because it relied on the perceived weakness of the material. The scrap steel wasn't meant to be impenetrable. It was meant to shatter the bullet's protective jacket, or induce the yaw and fragmentation early, dissipating the energy before the round reached the primary, stressed hull. It was a crazy trick that substituted time, skill, and scrap for specialized weight and material science. The pressure from the incoming landing operation was crushing. Reports flowed daily detailing the unsustainable loss rates among assault troops. Yet, the bureaucracy of naval repair demanded adherence to established practices. Processes that guaranteed absolute structural integrity, even if those structurally perfect boats sank because their occupants were dead. Mackenzie knew that official channels would take 6 months to approve a prototype of spaced field armor. 6 months that thousands of Marines did not possess. The decision solidified in his mind. This must be an unofficial project, fueled by necessity and salvaged materials. He started observing the yard scrap with the intensity of a prospector, identifying sheets of standard, non-hardened carbon steel that were too thin for structural repair, but perfect for his purpose. The entire framework of wartime engineering demanded slowness and calculation. Mackenzie's idea demanded speed and audacious, practical sacrifice of theoretical purity. He knew the risks of unauthorized modification were severe, court-martial potentially, but the cost of inaction was paid in blood. He began to feel a quiet, internal shift. The scrap steel, lying rusting and discarded in the repair yard, was no longer trash. It was potential. What he didn't know was that this simple, audacious idea would fundamentally change the war, turning logistical waste into life-saving defense, proving that sometimes the most effective solution is the one that utterly ignores the textbook. The problem of landing craft vulnerability was not a secret. It was an acknowledged historical tragedy inherent in the transition from protected sea voyage to exposed beach assault. Official reports from the Bureau of Yards and Docks, BUDOCS, detailing the performance of LCVPs during Operation Torch in North Africa and subsequent Pacific engagements painted a grim, statistical picture. Memo 41G, issued in late 1942, indicated that standard 1/4-inch mild steel armor plating offered sufficient protection against small arms, 30 caliber fire at ranges exceeding 500 yards, but was utterly inadequate against Japanese 7mm and 13 2mm heavy machine guns operating at the close ranges encountered in the final phase of a landing, typically 100 to 200 yards. The report meticulously detailed the ballistic properties. The high-velocity 13 2mm round possessed kinetic energy sufficient to pass through 10 of mild steel at 100 meters. The typical LCVP focused on maximizing cargo capacity, up to 36 men or 60 lbs of vehicles, simply could not spare the tonnage for robust armor. The Navy's attempts to solve this problem had been complex and largely unsuccessful in the time frame required. Prototypes focused on layering specialized manganese steel, known for its hardening properties upon impact, or STS plating, but these materials were scarce and prioritized for battleships and carrier flight decks. Furthermore, retrofitting existing LCVPs required complex dockyard procedures, demanding precision-cut plates and controlled welding environments, which were non-existent in forward operating areas like Guadalcanal or Samoa. An internal Navy War Office memo, dated January 1943, estimated that to adequately armor the approximately 14,000 existing landing craft would require diverting 30,000 tons of STS steel, a quantity deemed strategically prohibitive and logistically impossible. The scale of the logistical failure was crushing. For every 3 ships delivered from the U.S. mainland, only 1 could be fully maintained and protected due to the lack of specialized materials and labor in the field. The technical foundation of the failure lay in simple physics. Single-sheet armor defeats penetration only by thickness, demanding substantial weight. The Navy's standard solution was to increase the gauge, but this led to the engineering nightmare of stability loss and ramp failure. Shipyard data showed that adding just 2 tons of extra steel to an LCVP reduced its maximum speed from 12 knots to 9 knots, extending the time spent under fire by nearly 25%. This data, cold and numerical, confirmed a lethal spiral. Thicker armor slowed the boat, which increased exposure, which required thicker armor. Failed attempts included the use of sandbag reinforcement, quickly abandoned due to the instability and shifting weight, and the application of concrete mixtures, which cracked under vibration and added mass without sufficient ballistic protection. Field reports from the 2nd Marine Division's engineers were brutally concise. Current light plating provides protection only against splash or near-miss shrapnel. Direct fire from enemy heavy weapons renders the craft functionally useless, and the personnel deceased upon entry to the engagement zone. Immediate, rapidly deployable defensive modification required. This overwhelming factual basis, anchored in tonnage limits, production shortages, and specific ballistic data, solidified the problem. A solution had to be fast, light, non-specialized, and deployable entirely in the brutal, improvised environment of a forward repair depot, defying every conventional standard set by budocs in Washington, D.C. The need for radical, unorthodox innovation was mathematically proven by the sheer volume of lost equipment and, more tragically, lost lives. The cold precision of the casualty statistics translated directly into the raw, gut-wrenching experience of the Marines huddled inside the crafts. The numbers, the 65% loss rate within the final 300 yards, were not abstract figures. They were the searing memory of Lieutenant Wallace's platoon, shredded moments before the ramp dropped at Tarawa, caught in a crossfire that turned the LCVP hull into a meat grinder. The tropical heat, already oppressive, was intensified by the fear and the sickening realization that their transport, their vessel of hope, was essentially an unarmored target. Morale among assault engineers was flagging. They were mechanics assigned to a constant bloody salvage operation, pulling out gear and bodies from hulls that looked like Swiss cheese. Corporal Mackenzie remembered the sound most vividly, the high-pitched, tearing shriek as a 2 mm round ripped through the thin steel plating, followed by the wet, immediate sound of impact inside the cramped cabin. The wounded, often bleeding profusely onto the floorboards, faced interminable journeys back to aid stations, frequently exposed again due to the craft's open design. The weather itself seemed to conspire against them. Sudden squalls made precision welding impossible, yet the need for modified craft was constant and immediate. A powerful quote from a medic's diary, recovered after the chaotic assault on an unnamed Solomon's Island, speaks to the hopelessness. "We spent 3 hours collecting the dead from LCU 345. It looked like the enemy had used a can opener. We had the gear, the guns, the men, but the 5 minutes it took us to hit the beach in those flimsy hulls was a lottery nobody was winning. The men know it. They know the protection is a joke. How do you ask a man to run into hell when his ride there is already paper-thin?" The engineers, trained in structural integrity and precise tensile standards, faced the impossibility daily. They could patch the holes, but they couldn't stop the damage from recurring the next day. The traditional process of ordering, shipping, and installing factory-certified STS armor took months, an eternity, in the Pacific Theater's rapid-fire campaign schedule. The logistics chain choked on the demand for specialized materials. Mackenzie and his team worked 18-hour shifts, cutting patches, re-welding seams, only to see those same patches perforated again within 48 hours. The weight of human suffering pressed down on the technical specialists, creating an atmosphere where the pursuit of perfection felt morally bankrupt when pitted against the immediacy of survival. The consensus from every level, from the shipyard foreman to the naval architect, was monolithic and depressing. The problem was intrinsic to the design of the fast, shallow draft transport vessel, a necessary compromise of weight versus protection. To the men in the field, it was simple. They needed to stop the bullets, now. But the experts, the men with the degrees, the charts, and the theoretical knowledge of ballistics, were unified in their conclusion. Their voices echoed across the vast ocean, reaching the embattled repair yards with the finality of a death sentence. Experts agreed. It couldn't be done. The necessary combination of robust protection and minimal weight was mathematically and metallurgically an impossibility given the constraints of field production and available scrap. CTA. Before we continue following Corporal Mackenzie's fight against impossibility, take a moment to consider the sheer complexity of engineering under fire. If stories like this, where necessity drives unexpected innovation, fascinate you, stay with us. The next chapter of wartime ingenuity might surprise you. Thomas Mackenzie, born 31 years earlier in Duluth, Minnesota, carried the grit and pragmatic resourcefulness of the Great Lakes industrial belt in his DNA. He was the son of a crane operator and had left high school early to apprentice in the sprawling shipyards of Lake Superior, mastering the art of arc welding by the age of 19. Mac wasn't a theoretical engineer. He was a craftsman whose understanding of metal was visceral. He could hear the difference between a stressed weld and a true fusion. And he knew how much heat a piece of carbon steel could take before its structural integrity failed. His formal education ended where the practical work began, instilling in him a deep distrust of overly complex solutions that ignored the limitations of the working environment. When the war effort ramped up, Mac had voluntarily enlisted in the Marines, not seeking the glory of the front lines, but recognizing the dire need for skilled tradesmen in the engineering battalions. His expertise was quickly recognized, but his personality, a stubborn, practical streak that bordered on insubordination when confronted with what he considered stupid paperwork, often put him at odds with the rigid military command structure. Mac believed in the principle of minimum effective dose. Use the least amount of material and time necessary to achieve the desired functional result. This often meant his field repairs were rough, scarred, and ugly, but they held. His quirk was his obsession with salvaged material. While other repairmen waited weeks for certified Navy stock to arrive, Mac scavenged relentlessly. He saw the battlefield not just as a place of destruction, but as a vast, albeit deadly, parts depot. This background had taught him to improvise with speed. In the Duluth shipyards, deadlines were absolute, dictated by freezing weather or imminent delivery, forcing him to develop techniques for rapid, high-stress welding under suboptimal conditions. This resourcefulness, honed by years of industrial necessity, would become the foundation of his radical idea. He recalled one particular incident from his apprenticeship. A massive, pre-war freighter hull had suffered a catastrophic crack during stress testing. The chief engineer had demanded 3 days for controlled repair and annealing. Mac, then just 20, suggested a radical temporary repair using high-amperage welding to rapidly fuse overlapping plates, relying on the immediate cooling of the lake water to temper the outer surface, allowing the ship to meet its deadline. The resulting weld was ugly, stressed, and definitely non-standard, but it held long enough for the freighter to sail. That incident, years before, crystallized his belief. Theoretical perfection is often the enemy of practical necessity. His mind, conditioned by the rough, immediate demands of northern industry, viewed the meticulous, slow, bureaucratic supply lines of the wartime Pacific as an unacceptable weakness. A critical design flaw that demanded a quick, dirty, and effective patch, regardless of the rulebook. He saw the current problem of the landing craft not as a lack of specialized steel, but as a fundamental misuse of the steel that was already abundant. The endless supply of broken, salvaged, non-ballistic scrap littering every repair yard in the theater. The idea solidified not in an engineering manual, but under the blazing South Pacific sun, amidst the chaotic clanging of the Espiritu Santo repair depot. Mackenzie was sorting through a stack of twisted, discarded steel plate, debris from a recently torpedoed destroyer escort. He noticed the varying thickness of the scrap, some thin sheet metal, some robust quarter-inch carbon steel decking. He remembered the earlier test where the aluminum fragment had deflected the bullet. The key, he realized, wasn't the hardness of the material, but the geometry of the impact and the distance between the layers. The high-velocity round required a brief, violent interaction to destabilize it. His crazy idea was to install a protective layer of readily available, non-ballistic, quarter-inch scrap steel. This scrap, typically used for non-structural flooring or bulkheads, would be welded to the exterior of the LCVP hull, but crucially, it would be offset using 2-inch steel strips as spacers. This created a rough, improvised spaced armor system. The outer plate wasn't meant to stop the round completely. It was meant to shatter the bullet's hardened jacket and core, or induce a violent yaw, effectively fragmenting the projectile before the dissipated mass hit the main structural hull. He brought the idea immediately to his commanding officer, Captain Eli Vance, a career Marine who respected Mackenzie's skill but was bound by regulation. Vance listened, skeptical, his face obscured by the shadow of his field cap. "You want to strap scrap metal to half a dozen boats and send them into combat, Mac? That's the stupidest thing I've ever heard. If it shifts the weight even a fraction, those boats are compromised. We need stability, not your shipyard Frankenstein solutions." Vance's voice was strained, caught between the urgency of the casualty reports and the certainty of a reprimand from Budox. Mackenzie argued passionately, pointing out the availability of materials. "Captain, we have thousands of pounds of discarded plate that can be cut, rough-welded, and installed in under 4 hours per hull. This isn't perfect armor, sir. It's an emergency kinetic diffuser. It uses what we have right now, today, not what's sitting on a dockyard in California waiting for a 3-month shipping manifest." Vance remained unconvinced, citing the explicit prohibition against unauthorized structural modification to naval assets. But Mackenzie was determined. He decided to act alone, or at least unofficially. That evening, using the cover of the depot's chaotic night shift and the distraction of a major repair job on a destroyer's rudder, Mackenzie approached a reluctant former ally, Chief Petty Officer Harrison, known as Pops, a cynical but brilliant machinist. Mac convinced Pops that this was a matter of life and death, sidestepping bureaucracy entirely. They would appropriate the scrap steel, requisition welding rods and oxygen tanks under the guise of yard maintenance, and begin the work in secret, using the darkest corner of the repair shed where the shadows were deep and the official paperwork was non-existent. The determination in Mackenzie's eyes was quiet but absolute. The official word was no, but the cost of that no was too high to bear. The preparations for the clandestine test began under a veil of operational secrecy that rivaled any major amphibious planning. Corporal Mackenzie needed not only materials, but an isolated proving ground and someone to certify the test results without officially reporting them. He found his necessary accomplice in Chief Petty Officer Harrison, Pops, a man whose years in the Navy had taught him that sometimes the quickest path to safety was the path that bypassed the chain of command entirely. Pops, using his seniority and encyclopedic knowledge of depot supply codes, managed to requisition 200 feet of standard quarter-inch carbon steel plate, listed officially as temporary decking for yard safety. The secret setting was an abandoned, overgrown mooring area half a mile from the main depot, accessible only by a single dirt track. The heat was stifling, driving the air thick with humidity that clung to the skin like a shroud. Sensory details were paramount. The incessant, high-pitched whine of the portable DC generator that powered their arc welder. The smell of burnt electrode flux and hot slag mixing with the swampy smell of the jungle edge. They worked under the harsh glare of temporary floodlights, the only illumination in the oppressive tropical night, casting long, distorted shadows of their makeshift workshop. The planning involved meticulous calculation of weight distribution. Mackenzie realized that if the armor was placed too high, it would dangerously increase the craft's roll. He focused the application, the hedgehog-spaced plates, on the most vulnerable areas, the lower bow sections and the crucial frontal ramp structure. They used short, robust welds, concentrating the fusion only at the corners and centers of the 2-inch spacer strips, minimizing heat input to the main hull to prevent undue weakening, but ensuring the external plates could withstand the initial violent impact of a bullet. They cut the scrap steel into rough, diamond-shaped plates, each about 18 by 24 inches. The speed of the process was crucial to Mac's theory. The whole assembly for one LCVP bow section needed to be completed in less than 4 hours, or it failed the primary test of battlefield utility. "You really think 2 inches of gap and some rusty scrap is going to stop a 13-2, Mac?" Pops asked, wiping sweat and metal dust from his brow, his voice a low rumble above the generator noise. "It doesn't have to stop it, Pops," Mackenzie replied, tightening a clamp on a new spacer strip. "It just has to spoil it. Make the bullet waste its energy, turning from a precision projectile into shrapnel before it gets to the payload. It's about confusing the metal, not defeating it." The preparation scenes were taut with quiet urgency. They worked with practiced speed, the rhythm of the grinder, the clang of steel, and the intermittent blinding flash of the arc welder, creating a hypnotic, dangerous ballet. Every joint was checked, every spacer measured. They secured the experimental plates onto a salvaged LCVP bow section that was already earmarked for scrap, designating it Test Rig Alpha. They knew if they succeeded, they saved lives. If they failed, they had wasted critical resources and worse. Confirmed the fears of the conventional thinkers who insisted on following the rulebook to the letter, regardless of the body count. The only thing missing now was the definitive proof, the shock of the live fire test itself. The moment of truth arrived just before dawn, marked by a pervasive, tense silence that defied the humid air. Test Rig Alpha, the salvaged LCVP bow section adorned with Mac's rough offset plates, sat anchored 50 yards down the deserted beach. Mackenzie and Pops Harrison were joined by Ensign Dale, a young ordnance officer coerced into providing the necessary firepower, listed on his log as ammunition disposal training. The first test was against a single standard quarter-inch plate, the typical LCVP armor. Ensign Dale lined up a captured German MG-42, a weapon known for its high cyclic rate and penetrating power, a devastating symbol of the firepower they faced. Crack, crack, crack. 3 rounds hit the standard plate, The result was instantaneous and predictable, clean penetration, leaving 3 precise holes. The backing plate, representing the marine inside the boat, was destroyed. A grim silence followed. "See, Mac? Textbook physics," Pops muttered, shaking his head, reaching for his cigarettes. Mackenzie ignored him. "Change the target. Fire at plate section Gamma, the 3-strip spaced array, and Ensign, put the next burst directly onto the leading plate." The modified section used 3 narrow, offset strips of scrap steel, separated by exactly 2 inches from the main hull. This configuration was their gamble: less mass, more geometry. Dale adjusted the MG-42. Brrrrap. A short burst ripped across the target. Mackenzie immediately rushed forward, ignoring Pops's cautious yell. What he saw was revolutionary. The outer scrap plate was violently distorted, almost torn away at the impact points, scarred by deep, jagged craters. But the round had not penetrated cleanly. Instead, the high-velocity projectile, upon hitting the non-ballistic scrap, had violently fragmented. The outer layer absorbed the kinetic energy, and the bullet's core had either shattered into smaller, less harmful pieces, or had been deflected at a steep angle, striking the main hull obliquely. The main hull plating, a 1/4-inch mild steel, was heavily dented, scarred, and cracked, but critically, it was not penetrated. The projectile had been defeated by geometry and timing, not thickness. The fragments that made it through were now low-velocity splatter. Pops Harrison dropped his cigarette, the smoke curling forgotten on the sand. "Holy Mother of God," he whispered, awe replacing cynicism. "That junk actually held. It spoiled the round." Ensign Dale stared, his hands still trembling on the hot barrel of the MG-42. His report, which he would write entirely in unofficial shorthand, noted simply, "Field modification achieved 100% defeat of 7. 92-meter tungsten core penetration at 50 meters, utilizing improvised spaced plating." The shock was absolute. This was not a marginal improvement. It was a total, game-changing breakthrough, achieved with scrap metal and 3 hours of welding. The sheer, raw adrenaline of that first success was palpable. Mackenzie had taken impossibility and bent it to the will of practical necessity, proving that the solution to a complex, multi-ton armor problem could be solved by a few well-placed inches of nothing. If stories like this fascinate you, stay with us. The next chapter of wartime innovation might surprise you as we track how Corporal Mackenzie defends his scrap metal innovation against the Navy's most entrenched architects. The success of Test Rig Alpha could not remain a secret in a small repair depot for long. Within 48 hours, an official request, bordering on a summons, arrived from Rear Admiral Hayes, head of Pacific Logistics for Budox, demanding Mackenzie's presence at a high-level meeting on Guam. The confrontation was set in a sterile, temporary conference room, a world away from the grit and grime of the welding shed. Mackenzie, newly cleaned but still smelling faintly of burnt metal and flux, faced a tribunal composed of 3 naval architects in starched whites, and Admiral Hayes himself, a man whose stern demeanor implied a deep adherence to formal protocol and certified engineering. "Corporal Mackenzie," Admiral Hayes began, his voice dry and authoritative, "your unauthorized modification of naval property has been reported. We have conflicting reports on the structural integrity, and while Ensign Dale's unofficial ballistics assessment is intriguing, it violates every established principle of naval engineering. The added stress on the frame, the potential for non-standard material fatigue, it is a risk we cannot afford. One of the architects, Commander Stern, leaned forward, his demeanor coolly intellectual. "Corporal, the science of armor dictates homogeneous, hardened steel or complex alloy layering. Your use of salvaged, non-certified carbon steel, offset by what appear to be simple angle iron strips, is structurally unsound and ballistically unpredictable. Your methodology is, frankly, crude." The room was heavy with the controlled emotion of an intellectual clash. Mackenzie stood his ground, maintaining a rigid posture, but his internal conviction burned bright. "Sir, Commander," Mackenzie began, his voice controlled but passionate, "I respect the textbook principles, but the textbook hasn't been revised since we started losing platoons in the landing zone. We are not building a battleship, Commander. We are building a temporary shield. My method is crude because it has to be fast. We can fit out a dozen LCVPs in the time it takes the shipyard back home to cut the first sheet of STS for one hull. The weight increase is minimal, less than 1/800 pounds for a full bow section, well within the safety margin. The structural integrity is maintained because we are using short, low-heat welds, minimizing thermal impact on the main hull." He slammed the photographic evidence of the ballistics test onto the table, the deeply dented but unpenetrated hull section. "This round," he emphasized, tapping the photograph of the shattered projectile impact, "was defeated not by mass, but by physics. The projectile impacts the outer scrap, which shatters the jacket, creating a chaotic explosion of low-velocity metal that hits the primary hull as fragmented, dispersed energy. It saves lives, Admiral, and it uses waste. It is rapidly deployable, requires zero specialized material, and can be taught to any field welder in an hour." Admiral Hayes remained impassive for a long moment, reviewing the crude but undeniable photographs. The logic, stripped of academic theory, was powerfully simple. Mackenzie wasn't perfecting the ship, he was maximizing survival probability now. After a tense silence, the Admiral simply nodded, a sign of silent, necessary capitulation to undeniable field evidence. "Commander Stern," Hayes addressed his architect, "I want a full operational trial. Codename this the Hedgehog Directive. If this saves one hull, Corporal Mackenzie's crude methods will become immediate standard operating procedure." The intellectual battle was won not by superior rank, but by superior, immediate effectiveness. The transition from the meeting room on Guam to the sharp reality of the battlefield was swift and brutal. Within 2 weeks, 3 landing craft were clandestinely modified with Mackenzie's field expedient armor, now officially designated the Hedgehog spaced plating, and attached to the assault waves destined for the landing on Peleliu, an island notorious for its heavily fortified beaches and interlocking fields of fire. This was the real test, the proving ground where theory met mortality. It is September 15th, 1944. Hydro-8, 32 hours. The air is thick with the churning smoke of naval bombardment, but as the first waves of LCVPs approach the coral reef line, the heavy machine guns open up from positions the preliminary bombardment failed to neutralize. The modified landing craft, known only by their hull numbers, move in lockstep with the unmodified vessels. The cinematic pacing accelerates as the vessels hit the final 200 yards. The sound of incoming fire is deafening, a continuous, metallic drumming as high-velocity rounds strike the thin hulls. On the unmodified LCVPs, the results are tragically instantaneous. The sound of tearing metal is followed by the cries of the wounded, and the craft themselves begin to take on water from multiple hull penetrations. But the three Hedgehog craft behave differently. Corporal Mackenzie, observing from a command ship positioned slightly astern, watches through high-powered binoculars. As the enemy fire rakes the bow section of LCVP 788, he sees the distinct pattern of impact. Plumes of white-hot fragmentation explode outward from the rough outer scrap plates. The rounds are visibly disrupted, their clean kinetic energy dispersed and defeated. The boats shudder under the impact, the steel ringing like a gong, but they maintain forward momentum. There are dents, scrapes, and deep structural wounds in the outer layer, but the hull remains structurally intact, keeping the high-velocity fire from penetrating the vital compartment housing the Marines. The data gathered during the withdrawal of the first waves was staggering. Unmodified LCVPs in the first wave suffered an average casualty rate of 35% among the troops awaiting deployment, primarily due to fire penetration. The three Mackenzie-modified craft reported a combined casualty rate of just 5% and 0 complete hull penetrations in the bow and ramp areas. The modification, executed in hours with scrap, had reduced the tactical vulnerability by nearly 85%. The field report filed that afternoon was concise and delivered with triumph, restrained by military formality. Emergency Directive 7A, Hedgehog plating, confirmed to provide substantial ballistic resistance against 13, 2 mm and 7 mm high-velocity fire. Recommend immediate fleet-wide implementation for all forward-deployed assets capable of field welding. Life savings projected to be significant. Admiral Hayes, reading the report from his post, didn't offer a dramatic speech or even a commendation. He simply issued a one-word order that traveled through the chain of command. Implement. It was silent, official approval, a recognition that saving lives trumped bureaucratic perfection, the historical consequence of Corporal Mackenzie's simple, rapid innovation was immediate and far-reaching. The Hedgehog plating, codified under Emergency Directive 7A, was immediately disseminated throughout all forward repair depots in the Pacific and eventually to the European theatre. The simplicity of the process, requiring only standard carbon steel scrap, common welding rods, and a portable generator, meant that thousands of landing craft, from the small LCVPs to the larger landing craft tank, LCTs, could be retrofitted in a matter of days rather than months. The data proved the legacy. By late 1944, after the mass adoption of the technique, Budok's field reports showed that combat losses attributable to small arms fire penetrating the landing ramp and bow section had dropped by an average of 42% across the fleet. This technological adoption created a crucial strategic advantage, allowing assault troops to arrive on heavily fortified beaches with far higher tactical readiness and morale. The long-term effects resonated far beyond World War II. Mackenzie's improvisation formalized the concept of field expedient spaced armor. While spaced armor had existed in theory, notably on early tanks, Mackenzie proved it could be rapidly, crudely, and effectively manufactured using non-ballistic scrap, prioritizing speed and availability over metallurgical purity. This foundational concept would later influence the design of modular and applique armor used on military vehicles for decades, proving that two thin, offset layers are often superior to one thick layer of the same total mass. As for Corporal Thomas Mackenzie, the hero of this engineering tale, his life reflected the humility often found in great innovators. He politely refused the offer of a field promotion, stating that he was just a welder who hates patching the same damn hole twice. He continued his duty, traveling from island to island, teaching other Marine and Navy field repair teams the rapid hedgehog method, the quick cuts, the short high-stress welds, and the proper spacing, ensuring the knowledge spread by practical demonstration rather than through slow official manuals. He eventually mustered out after the war, returning to his shipyard roots in Minnesota, largely forgotten by the large-scale history books that celebrate generals and battleships. His legacy, however, remains etched in the rough, scarred steel of the salvaged LCVPs held in museum collections, each one a testament to the fact that the most profound innovation often comes from the lowest rank, driven by the immediate, desperate need for survival. The genius of Corporal Mackenzie's welding trick lies in its defiance of scale. Modern engineering, whether designing skyscrapers, rockets, or complex network systems, often seeks complex solutions for complex problems, demanding high-tolerance alloys and infinite precision. Mackenzie showed that sometimes the most sophisticated design is the one that utilizes the simplest materials and the fastest application. This principle, the pragmatic use of available resources to achieve maximum immediate impact, draws parallels to modern rapid prototyping and disaster response architecture, where speed and utility crush the need for theoretical perfection. Consider the complexity of a modern disaster relief effort. Specialized, perfect equipment is often stuck miles away, hampered by logistics. Mackenzie's lesson instructs us to look at the scrap, the local, available, imperfect materials, and apply an immediate, unconventional solution. This is the spirit of the keep it simple, stupid, KISS principle taken to its most critical wartime application, the pursuit of good enough right now rather than waiting for perfect too late. Mackenzie, the welding corporal, taught the admirals that improvisation is not the opposite of engineering. It is, under duress, its highest form. The rigid structures of bureaucracy and academic adherence to established standards often fail when confronted by the brutal, chaotic variables of the real world. His innovation was an act of translation, converting the language of theoretical physics into the common language of scrap metal and sheer human determination. The huts that once rose under shell fire, where Mackenzie and Pops Harrison first cut the scrap steel, may no longer stand today, but the dented, scarred hulls of the landing craft that survived Peleliu and Iwo Jima still remain, silent witnesses to a moment when a welder decided that his expertise was more important than the rulebook. These scars, these jagged edges of quickly applied scrap, are not flaws. They are badges of revolutionary necessity. They remind us that true progress often begins not in laboratories, but in the trenches, powered by the simple, powerful instinct to survive. Every great idea begins as an act of defiance against impossibility. What impossible ideas do you think could change the world?